Hi everyone. This video we're going to be learning about conditional proofs. So we're going to be comparing conditional proofs to the natural, to just using the rules of inference so far that we've learned in natural deduction. Now, the thing with conditional proofs is that conditional proofs use every single rule that we use in natural deduction. In that way, they're no different. What they're different in is the way that they're able to prove problems. Conditional proofs a lot of times will be a lot simpler than than just like straight natural deduction, and sometimes they'll even use less premises. I'm saying conditional proofs, but I mean like proofs in general. We're going to be learning indirect proofs in the next two videos. So right now we're just focusing on conditional proofs. So in this video we're going to go over two ways of proving this exact same problem, just using I'm not going to call this non-conditional proof. I'll call this just natural deduction. So natural deduction, and I'll call this conditional proof. Okay. So we're going to just prove this using the rules of natural deduction. So let's get started. So let's see, where do we start here? Well, let's take a look at the conclusion. We have Q then M. We see that I have Q in line 1, I have M in line 2, although it's like M or M. So, I mean, this looks like something that should be a hypothetical syllogism, but the hypothetical syllogism is kind of broken because, you know, there's a K right here, so I can't exactly just connect them. So where do I get started? Well, the most immediate thing I see is like this tautology in premise 2, so that's the first thing I'm going to do. So I'm going to get R or K, then M, and I get this through to tautology. Let's see, what's my next step? Well, I want to get Q then R or K. I'm going to need to do addition to get a K somewhere eventually. Before I do that though, what I want to do is I want to use implication to sort of break this up. So I'm going to get not Q or R, and I'm going to get this through one implication. The next thing I'm going to do is I'm going to get not Q or R or K, and I'm going to get this through for addition. Now that I have this, I'm going to get not Q or R or K, and I'm going to get this through 5 associative. Now that I have this, I'm going to get Q, then R or Q, then R or K, and I'm going to get this through 6 implication. Now that I have this, I'm going to get Q, then M. I'm going to get this through 3 hypothetical syllogism. So, I mean, we're able to solve this problem. It wasn't immediately obvious what we should do. I mean, but, you know, this is a valid problem. You know, we were able to prove it. So, I mean, even though it wasn't immediately obvious, we were able to solve the problem. But I mean, you know, there was a lot going on in this problem. I mean, one thing I want you to notice is that, you know, premise 3 and premise 4, for example, they both have 2 operators in this problem. I mean, now that might be something that we're used to at this point, you know, but I mean, every additional operator you have and every propositional statement you have right here, they complicate the problems. I mean, there's more written down, there's more going on, there's more you need to keep track of, and so again, we're able to solve this problem, but it wasn't that easy to do. So now we're going to take a look at solving them using conditional proofs. So let's get started. So conditional proofs start. Conditional proofs are typically used to prove problems that typically have their conclusions as the main operator of their conclusions as the conditional operator. So I mean, you don't need to use them to do that. Like later we're going to learn indirect proofs, and you can use conditional proofs and indirect proofs interchangeably as different ways to solve the same problems. But typically, if I'm going to use a conditional proof, it's going to be because the conclusion has a conditional as its main operator. Now, with conditional proofs, what you start by doing is you assume the antecedent of the conclusion. Now, the antecedent in this problem is Q. So we just list Q. We're just assuming it. We're saying, what can we solve if we had Q? So what we assume Q, and we justify Q by writing ACP. And ACP stands for Assumption for Conditional Proof. So we've assumed Q. Now let's see how far we can get if we assume Q. Well, if we have Q, then we can get R. And we get R through 1, 2 modus ponens. Now if we have R, we can get R or K. And we get R or K through 4 addition. Now if we have R or K, we can get M or M. We get M or M through 2, 5 modus ponens. And if we have M or M, we can get M. And we get M through 6 tautology. And so, as you can see, I mean, we got our conclusion M, but we're still not done yet. After we get the conclusion, the conclusion of our problem, the consequent, so we assume the antecedent, and as a result, we've assumed the antecedent of the conditional, and we've gotten the consequent of the conditional, which is M. So now we just need to restate the conclusion, which is if you assume Q, then you can get M. And we did this using lines 3 through 7, and we did this using a conditional proof. So that's how you write. You write the lines that you used to prove this, which are lines 3 through line 7, and the proof we did was a conditional proof. As you can see in our premise 1, which is an assumption for conditional proof. So let's compare these two methods. So, I mean, as you can see in the first problem, the natural deduction, I mean, we have at least 2 operators in every premise except for the conclusion. And in some cases, we have 3 operators. And we have a lot of propositional statements. In premise 5, we have 3 propositional statements. In premises 5 through 7, we have 3 propositional statements. And in premise 3 too, there's 3 propositional statements. And in premises 5 and 6, there's 3 operators. I mean, there's just a lot going on. Now let's compare that to the natural deduction. Let's compare that to the conditional proof way of solving it. Well, in a lot of these, there isn't even one operator. I mean, in premises 3, 4, and 7, there's no operator, and it's just a propositional statement. And where there are operators, the operator is limited to just one operator, as you can see in premises 5 and 6. So, I mean, there's less going on. It's simpler to do. It's easier to read. I mean, even, I don't want to say that there's simpler or harder rules of natural deduction, but I mean, modus ponens and addition are some of the easier rules to use as opposed to ones like implication, and to some degree associativity, and and also like reversing implication. And so I just think it's pretty straightforward that the conditional proof way of proving it is a lot easier to do and a lot simpler to follow. And so these are some advantages to using conditional proofs. Now we're going to be taking a more detailed look at solving some more conditional proof problems within the next video. So I'll see you then.